Okay, so let's go over the warm-up. I'd like to know your thoughts. With a show of thumbs, yes or no? Was there ever a time in your life when you were exactly 5 feet tall? I've seen some yeses and nos. I'd like to explain why they think they answering is what yes, Rowan.
The only way you could be exactly is if like you were at one between growing from 3 and 4, you were like every height in between that,
Mhm.
literally. But even if like let's like
Wait, so you're saying at one time in your life you were 3 feet tall? And would we say in everyone's life we were 3 feet tall at one time in your life? Are you sure? Do you remember the day? Were you measured? You're measured at 3 feet?
We don't need to be measured.
You don't need to be measured. You know there was a time in your life when you're 3 feet. And you're saying four or also four. Okay, so you're saying at some time in everyone's life there were everyone here, 3 feet tall, 4 feet tall. Okay, and proceed.
to like be able to be exactly pi, you would have to be every like height in between that. But like you at like the base level, it's like if you're growing by like one, even by like one cell, that's like too large of a increment.
Interesting. So it's too exact. Okay. Any other ideas?
You can't like you can't skip a height because you can't go from 3 feet to 4 feet
Mhm.
like just like that.
Okay.
You have to like hit every number in between. That includes pi.
Okay. So since pi is like right here, and is pi an actual place on the number line? What do you think? Is it an actual place on the number line? Or does it like vibrate or something?
Actually, sorry.
It's an exact place, right? That a lot of people are like, well, it's so interesting because like this number goes on forever, but three also goes on forever. It has to be super exact, doesn't it? Like you have to have zeros forever to be exactly three. So yeah, three has a place, pi has a place, 3.5 has a place. So you're asserting that you can't jump a
Or like how
height.
small. Like maybe in reality,
Mhm.
like the cell point was like probably true, but I feel like you can't skip any.
So even if it's a cell, maybe in that
Yeah.
growth,
If it's like a fraction of like a millisecond,
uh,
you were that height, you're still that height.
any other thoughts? I haven't heard the cellular thing. That's pretty interesting. Um, I think it's generally considered that you can't skip a height. That you just can't. There's no one's ever went to 3-1 to 3-2 in an instant. I think not as far as I know. And when does your growing happen? Do you know? Yeah, when you sleep, that's when your growth happens. Okay, so it's generally accepted that there is a time in all of our lives, as long as we surpass pi feet, that we do get to pi. But I like this cellular slant on it. That's really interesting, insightful. Because most people say no because pi doesn't exist on the number line, which is not true. There's a very specific place for pi. Okay, this one. This is a little bit of a throwback. I like some help from the one and the only. Hiya, can you help me with this, please?
Yeah. I kind of did it factoring by grouping. So I factored x squared from that, and I got x minus 4 parentheses, and then I took out a -9, got -9 parentheses, x minus 4. And then I factored by grouping, so I got x squared minus 9 times x minus 4. And then it's a difference of square, so I did x plus 3, x minus 3, and x minus 4.
Are we good with this? That was nice. Thank you. Okay. So this unit, do you know what the name of this unit is? Polynomials. We've studied polynomial expressions, haven't we? Like if I say cubic, the number that comes to mind, of course, is 3, and that 3 has to be an exponent, yes? If I say quadratic, the number that comes to mind, quadratic, in the term of polynomials, the number that needs to come to mind is 2, because x squared, that is quadratic. So this whole unit is going to be about quadratic functions. You guys okay? And a function is just remember something that has an input that is paired with an output. And we've talked about two different polynomial functions so far, haven't we? Linear, which is always in the form, well, it could be written in the form mx plus b. Quadratic, ax squared plus bx plus c. But polynomials, and I'm going to try to get through as much of this as I can today because we're a little bit behind. The polynomial function is just a function in this form. I think in the past we've not had that f of x, and maybe we didn't have all the other stuff here. But all this is saying is that it can be written in this form. Notice the first term has an expression, excuse me, a coefficient, and it has an x with a exponent. And then as we proceed, that exponent decreases. Now, do we know what n is? Let's see what it says about n. It doesn't say anything about n, does it? It says non-negative. Does it say that?
Yeah.
Where does it say it? Oh, and n is a non-negative integer. Okay, so those all had to be positive. Okay. Do we know how many terms it has? We don't know how many terms, just it could be written in this form and is any non-negative number. So let's take a look at some examples of polynomials. Like A, is this a polynomial function? It doesn't have all the other terms, but it just needs to have one to be a polynomial function. Yes, this is a polynomial function. Do you know the degree already? It's the second degree. So yes, degree 2. B, is that a polynomial? There's a little bit of an issue. Specifically, it's the -1. A polynomial has to come from a cluster of multiplication. By definition, that x and -1 is 1 over x, not a polynomial. Nope, not a polynomial. We're not even going to try to give it a degree. What do you think? C, polynomial? What's getting in the way of that being a polynomial? Yeah, it's a big fraction. Definitely not a polynomial. Nope. So 3, is that a polynomial? This one is, and it just like from this definition of polynomial, it just has a single term. It's just that last one. And that's okay. So it qualifies as a polynomial. So yes. And the degree is it 1? We check with your neighbor. It would be 1 if it were 3x. It'd be 1 if it's 3x. This is not 3x. This is just 3. So that's why the degree is 0. You could think about it as 3x to the 0 and not change it, can't you? Does that make sense? It's the same thing. And from there, you can see the degree. E, is that a polynomial? Should we multiply it out and check to see if we could put in this form? That seems like a huge waste of time if it's just asking if it's a polynomial, don't you think? Obviously, it could be written in that form because you know the distributive property. So we're not going to do that, but I think you already know the degree. Would you please hold up the degree? I'm saying different thing. Go ahead and discuss. How would you get the degree here? Okay, show me the degree again, please. Thank you for changing those 5s. The degree is actually 8. And it comes from what would happen if you were to multiply it all out. Should we multiply it all out to check? Only if you really like wasting time. I'm not going to do it. But you can just see, taking 3x, well, just x squared times x to the 5th. Done. X in the 8th column because that x, it does have a first, it has a There's a 1 on there if you were to multiply it all out. Yeah, Jihan?
There's a quiz. I had a question about the quiz.
Oh. Oh, not today. Thank you for reminding me. Next time. F of x equals 0. Is that a polynomial? Yeah, it is. Degree? This one is special. And I'll talk about why. This is not degree 0. In this case, a degree is none. It doesn't have a degree. It doesn't have any degrees. And yeah, remind me to talk about that later. I'm not going to put that on the test. It's not going to be a gotcha for a test or for a quiz. But you do have to know that any other number, the degree is 0 because it could be written as x to the 0. I guess maybe we could think about this. This is also x to the 5th, isn't it? Isn't that still 0? Is it? I didn't change it. This is also x cubed or x to 0. It doesn't have a degree. That 0 kind of nullifies that whole exponent of the x. So that's the rationalization. But yeah. Yeah. That's what I'll say it is for now. Maybe I'll talk about that more. Graphs of polynomial functions. You already know what a linear function looks like, don't you? Show me what a linear function looks like. Yeah, it's a line. A quadratic function, you already know what that looks like. Quadratic function looks like you have your pocket parabola, bam, or bam. Okay. So we're about to get higher than that. We're about to go above quadratic. And just so you know, polynomial functions always look something like this. They're called well-behaved. Look how smooth they are. Look how nice they are. Look how they connect. Every dot has one right next to it. As opposed to these poorly behaved. Are these even functions? How do you know they're functions? They definitely pass the vertical line test. So they are functions. But notice they have strange features on them that the polynomials don't have. They have things like corners and jumps like that. No polynomial is going to look like that. So when we're graphing polynomials, just make sure it connects and it flows and there's no corners on it. Agreed? But that's big picture stuff. Big picture because it's important to keep in mind. Okay, this says calculator. Like, we're not going to do calculator today. I'm sorry. We're going to do brain. So I'm going to cross all this out. So I'm going to cross all this out. I just want to look at functions with you quite simply. F of x equals x. Would you show me exactly what this looks like? Oh, you need the space. You need the space to work. F of x equals x looks like. Show me what f of x equals x looks like. And make sure it's matching your neighbors. Yeah, it just looks like this. It's y equals mx plus b, so y equals x plus 0. Whatever you put in comes out equally. F of x equals x squared. I know you know what this one looks like, but this is where I want you to put your pencils down. Just put them down for a while. Now, f of x equals x increases, right? The first one that we did, but equals x squared. This one increases too, but it increases faster, doesn't it? And of course, it increases faster because the x value is being squared, right? That is going to get bigger faster than if it's just x. And you know that the other side goes up, but my question is, why does that one go up? Let me just check with your neighbor. Why does that go up on the left? You got it, right? It's kind of simple. It's yes. I'm not even gonna to ask. If you're not sure why it goes up, please talk to me after class. So we have done x cubed, haven't we? It's one of our parent functions. And this one is here. This increases, but it actually increases compared to the parabola. It increases faster because x is being cubed. We'll get to exponential later on. And of course, the other side goes. Why does it go down? Yeah, it's negative because when you cube a negative number, the result is negative. So I do want you to notice that here when this comes down, this just touches that x-axis as opposed to this one, which goes through that x-axis with a twist. What do you think, Kai? Does that make sense? One touches, the other one goes through with a twist. And we're going to see that a lot in this unit. If I ask you to show me f of x equals x to the sixth, could you give me a rough sketch of that? Check with your neighbor. What would that even look like? Why f of x equals x to the sixth? Show me what it looks like. Kind of looks like a parabola, except it's gonna be really skinny because those values are going up high. Is that what you're imagining? And we could use our calculator for that, but the calculator you have in your head is enough. It's just gonna go, it's gonna become vertical? Why not? Yeah, the x cube changes. If it becomes vertical, then it fails the vertical line test. So it's definitely not gonna get vertical. I'm gonna make sure that in my notes, I'm gonna make it look so it's not gonna be vertical. I hope that in yours too, you don't ever have vertical lines in your functions. Do you have any idea what f of x equals x to the 11th might look like?
Oh, yeah.
Show me what it looks like, please. You might have to use your whole body, right? Oh, something like this. Goes up on one side and down the other. And we know that because 11 is odd. So it's going to do something like this. Let's do one more. F of x equals negative 4x to the 8th power. What does that look like? Just super rough sketch, super rough. And show me what it looks like, please. Just with your gestures. What do you think that would be? So it kind of looks like a parabola opening downward, except super duper skinny, right? Okay. So see what I mean? We don't need a calculator to tell us these things, that if the exponent is odd, we're going to have end behaviors, what they're called. If the exponent is odd, can you show me what the ends of these are going to look like? If it's odd, it's going to either be this or this, right? Depending on that leading coefficient. And if the exponent is even, it's either going to be up. Oh, I use my pocket. Grab mine. Either up or down. Okay, like this one we know is definitely going to be down. And this is a terrible sketch, but it's exactly what I need just for general shape. If I want to get some points, we could get some, but we're just looking for an idea of what's going on. Connor, what do you think? 2 thumbs up so far? I feel like you're vibing with this so far. Okay. I don't know about the rest of you though. So let's move on to this. Leading coefficient test. Okay, so what this is saying is, notice these functions have suddenly gotten much more complicated. But don't worry, it's not that bad. We're just talking about the end behavior of the graph of the given function. So which is the most powerful term in this polynomial? The x cubed, isn't it? So no matter what happens, as x gets bigger and bigger, and I want you to listen to this. Don't write anything down. As x gets bigger and bigger, these three terms here become less and less important, or the less and less powerful compared to the x cubed. For instance, if you plug in a 10, that first one is, what is 10 cubed? It's 1,000 compared to 300, and then just measly 10 and a 3. And if you were to plug in like 100, this is huge compared to that first term, is huge compared to the other ones. So what happens here is that ends look like f of x equals x cubed. So I don't know what's happening in the middle, but as x gets bigger and bigger, as x gets smaller and smaller in the negatives, it's going to look just like x cubed, which does something like this on that side and this on that side. What do you think? Is that clear? Like we haven't studied polynomials like this, so we can't graph them yet. But we do know that since x cubed is the most powerful, eventually it's just going to go up there, down here. That x squared is going to do some monkey business in the middle. We don't care about right now. So for the end behavior, I would do this. For now, I'm just going to do this in notation. So this would be the end behavior. Do you see that this is just what I'm talking about here? And we could put this into words. This one is as x goes to infinity, y goes to infinity. As x goes to infinity, the y's are going to infinity. For this one, we could say as x goes to, in this case, x is traveling along this way, isn't it? X is going to negative infinity here. Y is going to negative infinity, going down that way. So you could show the end behavior with notation like this, or you could write it in a little bit of a mathematical sentence. We do make sure your neighbor is okay with that, and then see if you could figure out C. C. Go to C next, please.
Yes. Sure. I have a question. Trust that consider for like like access infinity y is infinity or like the access negative
No, like the left one.
y is negative.
Every polynomial has two ends. So
So it can be both.
it's both this or this if you just want to graph it.
Okay.
Okay, yeah, let's talk about A. Perhaps that wasn't perfect here. Use a leading coefficient test to determine the end behavior of the graph of the given function, which means we just look at this. We just look at the leading term, that x cubed. And based on that and our own knowledge of x cubed, the ends of this polynomial will resemble that of just x cubed. So the answer is either this, if it doesn't specify how to answer it. Come on, let me select another color. Oy vey. Right, this is fine. This little box right here is a good indicator of what the end behavior is. Or you can write the same thing. If it says to use statements, you can see these two will be the answer. Can you show me the end behavior for C? Can you show me the end behavior? Yeah, it's the same end behavior as x to the fourth, which we know looks like this and this. So that's a fine answer if it doesn't say how to answer it. Does that make sense? Now, there may be some craziness happening in the middle. We don't care about it. We just care about the ends. How do we say this, though? Like this last one would be as x goes to negative infinity, y goes to infinity. The right one would be as x goes to infinity, y goes to infinity. Try B and D. Should you multiply it out? All you need to know is which term?
Next to the.
The leading term. You just need the leading term. So do not multiply it all out. But make sure that you and your neighbor both know the leading term.
You just look at that. It's cute or what is it? If we did multiply it out, we're gonna do the still less. Like the feeling. Six. Yeah. Yeah, so what do you do?
Can you please show me the exponent of this polynomial for B? Don't forget, when you multiply this x, it counts as a full x. So yeah, so this looks like y equals x to the 6. Oh, it doesn't look like positive x to the 6? Negative 4. You don't have to have the 4, but the negative is super important so that we can see. Can you show me the end behavior, that negative 4x to the 6, please? Yeah, it's just going down in both directions. So there's a picture worth 1,000 words. I do want you to write the other two statements. I will be calling for someone for D in just a moment. Are you ready to be called on? You guys are fast. Maddie, can you help me out? D, please. Do we agree? Does everyone agree with that? How do you know that they go opposite? Nice. Yeah, ultimately it's an odd exponent. Were you able to write sentences for these? Let's write that together. So as we have two of them, x goes to negative infinity and as x goes to positive infinity. As x goes to negative infinity, what's happening with the y's? Negative infinity. And as x goes to positive infinity, y is going to what? Positive infinity, right? Any questions? Okay, moving on. So we're going to try to reel our graph in a little bit. And in order to do that, we have to talk about the zeros of a polynomial function. And I think I talked about the zeros last time when we were graphing the parabolas from factored form. Zeros just mean when the function is equal to 0. That's why it's called a zero.
It's just the x.
So it's a perfect. Yeah, that's another way of saying it. The x-intercepts is another way of saying zeros. And sometimes I'm going to slip and I'm going to call them roots. They're also called roots. So zeros are the same as x-intercepts. That's another way of saying it. Or roots. Okay, so this polynomial, you can see it has how many zeros? It has 4. And the behavior at these zeros is different for these. So like for these two, it crosses it. Here, we're going to say it touches it. Please do not use the phrase bounce off. It touches it. They're very different things. Bouncing implies that there's some sort of a corner there, but it needs to be touched. Just like the parabolas would do. And this is a cross. Some of these are below the x-axis, some are above. I think you can tell which is which, and it's shown there. Easy. Okay, let's keep going. Definition: if f is a function and r is a real number for which f of r is equal to 0, then r is called a real zero. Ooh, real zero, as opposed to imaginary zero of f. So we're only going to be talking about real zeros of these polynomials for now. This means the following statements can be made as a consequence of the definition. R is a real zero of the polynomial function f, or R is an x-intercept of the graph of f. So how do we find the zeros of a function? Well, we need an equation to solve. Right now it's a function. We need to set this equal to 0, and now we have something we could solve. Go ahead and do it. Make sure your neighbor got it when you're done, and then move on and do the other three. We call in 4 people for answers in just a moment. I'd like to make sure you're on the right track for A. I just want the answer. Karen, what'd you get? Yeah. 1, -1, and 3. Do we agree? Thank you. What's that? Oh, did you say -3 or 3? Okay, I wrote poorly, excuse me. Negative. Okay, yeah. 1, -1, negative. If I'm going on calling someone very soon, maybe I'll do B already because you should have gotten through B. Connor, what'd you get for B? Negative plus or minus 2? Okay, plus or minus 2. Negative, positive. Okay. Is that it? Are we good? Is that it? Plus or minus 2? Okay, thank you. People are still working on these. Fine. Just a little bit longer. Okay, for C, Roland, what'd you get? 0 and 2. Thank you. Do we agree? Keisha, what do you get for D? Do we agree? Any questions? Okay, easy stuff. Zeros are actually pretty nice to find. Multiplicities of zeros. Okay. I think I'm gonna do this by example instead of write a bunch of words. I'm just gonna do an example and tell you what the multiplicity is because it's pretty straightforward. Can you show me the degree of example 4, please? Show me the degree. Show me, show me. I'm glad to see no one's holding up a 2. And it seems like you guys have figured out that the x has a variable. And this is, sorry, no, it's degree of 3, right? When you multiply this out, you would get an x squared. And then when you multiply that by that x, you get x cubed. So it definitely has a degree of 3. Okay, can you show me the end behavior of the graph of f of x? Can you show me? Yeah, the leading coefficient is positive, so it's going to be exactly like our normal x cubed. It's going to look like this and this if I'm drawing pictures of it. Easy. Here comes the fun. You ready? List each real zero and its multiplicity. Okay, well, there's -1 and the other 0 is 3 over 2. Do we agree? This one has a multiplicity of 2. This one has a multiplicity of 1. Now, where did that 2 come from? It's just the exponent on the 0. That's it. You could say mult of 1. If you want to write it out, you could say multiplicity. You could use like the multiply sign if you want. I don't mind. If it's in context, I'm okay. I'll know it's not an X.
Means it's because there's 2 on top of it.
Yeah, it means that this 2x minus 3 is actually there twice. It's called multiplicity 2. If it would have been cubed, 3, right? It's super simple idea. How many zeros are there? Determine whether the graph touches the x-axis at each intercept, touches or crosses or touches. So I'm just gonna graph this for you, and then I'll show you how to put in the touch or the cross. We have 2 zeros at -1 and 3 halves right there and there. And I'm going to use my end behavior, right? It's in my head. Say, okay, it's going to go up this way and down this way. Now, when it's multiplicity 2, it's going to look like a little parabola at that 0, which means it's going to just touch it. So like here, I knew that it's going to go up from here, but it's not going to cross it. Because it has that multiplicity 2, I know it's going to touch it. So 3 halves, I know it's going up from there. Multiplicity 2, I know it's going to act like a parabola. It'll act like a parabola there. Just touch it. Which means at that other 0, because we know that the end behavior is going to send it down, it's going to cross it. And that's always going to happen when it's multiplicity 1. Here we go. Mult 1. Mult 2. And we've graphed a pretty meaty polynomial now. Any questions? Yes, Connor?
How does the multiplicity to make it a graph?
Good question. Yeah, if we were to plug in values before 3 halves and after 3 halves, let's try it. We plug in a 1 and a 2. Notice if you plug in a 1 into this, you get a -1 on the inside, but then you square that, it becomes positive 1. And if you plug in a 2, you get the same thing, just like in a parabola. And that's always going to happen. Do y'all see how that works? On either side of that 0, if you plug in values, it's going to have the same behavior because of that square. Yes.
So what if it means this?
Nice to say, multiplicity. See, that kind of question is really how you ensure that you keep learning. And when you extend the concept like that, we're going to talk about this. So thank you. That was really nice. And I want you to always, when you're doing your homework, also like, what if this question had this twist on it or this twist, right? Because once you do one level, you know, I'm going to crank it up a little bit. And that's exactly what I'm doing. And we'll talk about that in just a second. But that was beautiful. I love it. Any questions up to here? Perhaps your question is, can we try some more? Okay, I think you could do just do A and B. We'll graph it together.
After just that behavior, can you just do the arrows?
Yeah, that's fine. And you're just doing A and B so far. Check with your neighbor because I'm about to call some people. For A, there's a question you have to ask yourself before behavior, right? What's the key question, like the word? The degree. Did you all ask yourself, what is the degree of this polynomial? Did you ask yourself that? Okay, for A, can you please show me the end behavior? Okay, so I'm seeing this. Is this right? Like that? Right, that leading coefficient would be -4, and we know it's x to the fifth. So yes, that's definitely the end behavior. Each real zero and its multiplicity Feliciano. The real zeros, please.
5 has a multiplicity 3, and -1/2 is a multiplicity 2.
2. Are we good with these? Okay. Do we know the graphs of any other functions with multiplicity 3? Do you know any? Yeah, just x to the third. Isn't that a 0 with multiplicity 3? This one over here. Isn't that a 0 at 0 with multiplicity 3? Anytime it's multiplicity 3, it's going to look like that. Not only is it going to cross through, it's going to cross through with twist. Or it's going to be flattened out. So could you already put this together? We start with the end behavior in our heads. We start with the end behavior. I know it's going to go up here. I know it's going to go down here. I know the zeros are -1/2 and 5. Bless you. I get excited when I'm doing polynomials too. So you see what's going to happen at 5? Is it clear how I knew that? It's end behavior. And not only is it gonna, I'm not gonna do this. That makes it look like multiplicity 1, just going right through it. That looks like multiplicity 1. So because multiplicity through 3, it's going to cross through with a twist, which means I have to do this kind of thing. And I do want this kind of nuance on a test or quiz. I'll let you finish this graph if you haven't already. Yeah. Oh, I don't know. It's your neighbor. Yeah, check with your neighbor when you're done. Okay, so perhaps what you drew at what's happening at that negative one half? Can you show me what's happening at the negative one half with the function? Yeah, it's just bouncing off it. Not bouncing, excuse me. It's gonna touch it and then go like this. Is that clear? Notice what I don't care about at all. I don't care how tall that is. I don't care how steep this is. I don't care about these things. I just care about the behavior of this polynomial graph. I care that it doesn't have any corners, it doesn't have any breaks, it's well behaved. To make sure that yours is too. Oh, because that's nice. How long have you been graphing polynomials? Is this a hobby of yours? Um, let's go on to number 6. If you want to go right to the graph, you can. Sure, neighbor is doing this correctly. Yeah, again, check with your neighbor, check with the people in front and or behind you. That's right. You should all have similar answers.
So constant.
Because that's the end.
So I think it's like this.
Goes on time. They want to say go over.
Okay, first step. Let's talk about this. Determine the end behavior. Show me. Show me the end behavior. And you know, it's going to be the same end behavior as that of any cubic function, and it has a negative leading coefficient. So I think this is what you were showing me. Are you okay writing that as x goes to, then y goes to? You need to be able to connect those. I just don't want to waste your time here. And a really big thing here is to have a big picture. This means something. That end behavior just means that over here it's going to be going down, over here it's going to be going up. And not necessarily in those quadrants, just in the scope of the polynomial. I need some help graphing this now. So Isabella, can you help me kind of reel this together? -2 and 1. Do we agree? Okay, are you comfortable continuing? Okay. So I could take my end behavior and just kind of do this, is what you're saying? Do we agree? So just touches too? Okay. Just kind of like, oh, I'll do a better job. Like that. So I have that my end behavior, right? My notes on the end, they came to fruition, and the multiplicity has been taken into account. Now, sometimes you're going to get a little bit confused, and you might do something like this if you have end behavior wrong. Do you see that? How you might before, if you mistakenly think that the end behavior is going up in both directions. Do you see what I had to do that's so wrong here? I introduced another x-intercept. There isn't one. So don't force your answers. You know, if something isn't working out, figure out what your error was from before is this one definitely, as Isabella already told us, just goes down forever. Bam. Is this pleasant? I hope that the concepts are not too complicated as long as you're handling it one at a time. Any questions? Perhaps your question is, can we try another? I'm not sure. I think that we're talking about turning points now. Sorry, you'll get plenty for homework. Turning points are places where the polynomial turns. I know, mind blowing. For instance, this polynomial has how many turning points? What do you think? Just it has 3 turning points because it turns around and goes back the other way. Yay. Okay, here's the thing you need to know. If a polynomial function is of degree n, then the graph of f has at most n minus 1 turning points. Think about what you already know and how this makes perfect sense from what you already know. Will you check with your neighbor where you already know this? Polynomial n is n minus 1. So the most concrete example in our heads that we have already that we know is parabola. We know degree of a parabola is second degree, but it only has 1 turning point. Yes? So if it's cubic, that means it could have at most 2 turning points. And I'm going to put an underline there, which means it can't have more, but it might have less. For example, I think you already know the function y equals x cubed, don't you? How many turning points does that have?
2.
Let's see, it looks like this, doesn't it? How many turning points does that have? Returning means it has to go the other direction. So this actually has 0 turning points. Right? A turning point literally has to go back the other direction. So a cubic might look something like this also, but this is no longer x cubed. But see how many turning points there are here? There's 2. There's 2. Here's a turning point and here's a turning point. So every polynomial can have at most n minus 1 turning points. So let's take a look at these. Which of these graphs could be the graph of that? Ooh, this is a good one. Check with your neighbor. Well, think about it. Think about it. And when you're ready, check with your neighbor. And you have people in front of you and or behind you. If you finish discussing, please open up that discussion. Can I call on someone? I'm well. You had that chance to discuss. I'm calling. McKenna, been a while. Okay, so here or here. And so can you go over your thought process, please?
5 checkpoints and -1. This graph is 3. So that don't work.
Yeah, this would be like x to the 6th power, right? some sort of six. So definitely not this one. Okay, and D. Nice. Okay, so did anyone else go through that same thought process? It's not this and it's not this. Do you have a question? I don't want to answer yet. Do you have a question? I don't want to. I'll give you a chance in a moment. McKenna, do you have anything else about this? Trying to figure out these two. Okay. Just wanted to make sure. Roll, do you have some input or some?
Tell that speed because of the y intercept.
Oh, how do you get the y-intercept? Ah, does that make sense, folks? Nice. Yeah, it's a quick clue. And we're not going to try to find the zeros of that unless you really need to. But yeah, that's a big difference. This is positive, this is negative, and we could see that from our function, the y-intercept has to be negative. Right? So maybe in our notes, we should go back to the beginning and illustrate that. Well, we did a lot today. So in this polynomial, perhaps we should say that, how should I write this? I want to write the y-intercept stuff. How can I put that in my notes here? Well, it has to be meaningful for you. Where would you put it here? It's rolling for 300. A sub. Do we see that? Right? If you plug in a zero, all the other terms go away except the last one. So yeah, this is the y-intercept. Good catch, Roland. Thank you. Okay, we have one more concept to talk about. Wow, we are just looking through it today. We were a little bit behind, so this is good. Okay, put your pencils down for a moment, folks. Just enjoy this mathematical story I'm about to tell you. Kai, you with us? Yeah. Here's a story about a well-behaved function. Are you ready for this? It's not an exciting story, I'm sorry. But I will tell you that if I plug in an a, this is f of a, which means the point I have. And I'll give you a moment to write this down a little bit later. And if well, if this is b and this is f of b right here, so far so good. What the intermediate value theorem tells us is that if this function is well behaved, somewhere between a and b, there'll be a value that hits every number in between f of a and f of b. And in other words, is it guaranteed that the function will get somewhere like up here? No. Is it guaranteed that the function will be down here? It could, right? It could come down and do that. But what is guaranteed by the intermediate value theorem is that it will definitely hit this point, and this point stands for any point in between these. Does that make sense as an idea? The intermediate value theorem says to go from here to here, it has to cross through every single point that is intermediate for f and a and f of b. I'll give you a minute to catch up with the sketch, and then I'll put the words. Put some other notations in there too. Oh, not a turning point. It could be. Can you imagine a function resulting in more than one place where it hits that f of c? For instance, it could do something like this, in which case it actually hit that value 3 times. So intermediate value theorem, and I'm not going to put this into words right now. I'm just going to put this into pictures. I'm going to let you put it into words. Intermediate value theorem just says if a function is well behaved, it's going to hit every y value in between the endpoints of the function. Now, let me show you how this is going to be used. Show that the polynomial function f of x equals x cubed minus 2x minus 5 has a real 0 between 2 and 3. Well, another way to talk about real zeros is, here, make sure to do that later. A real zero is another way of saying x-intercept be blocked in. I like this. So to do this, I'm going to put a 2 here and a 3 here. And I'll figure out what f of 2 is and what f of 3 is. Well, when I say I mean you. Would you please figure out what f of 2 is and f of 3 is? Check with your neighbor, what your neighbor got, and see if you can figure out how you're supposed to do this problem. Could you show me what you got for f of 2? Is it showable with 2 hands? So -1. F of 3, can you show me what you got for f of 3? Isabel, what is it? 16, is that right? So if I want to graph this, I would have a point over here. This is 2. And then a point over here. So how do we know that there is a 0 between 2 and 3? I want you to discuss with your neighbor in words. Now, how do you know that there's a 0 between 2 and 3? So how can you put this into words? That, is it obvious that there's a 0 between 2 and 3? Is it obvious? So how do you put this into words? Because I know that's the hard thing in math to do that. One of the hard things. Yes, Jihan.
Oh, in order for f of 2 to reach f of 3,
Mhm.
it has to cross the x axis.
Do we agree? Are you sure that this function is well behaved, though? That's only if the function is well behaved, don't you think? Maybe it's going to jump over it. Do we know this function is well behaved? I like what you're saying. Roland, do we know it's well behaved? Yeah, it's no negative exponents. We know the function is polynomial, well behaved. It definitely has to cross that x-axis, which means there is a 0 between the 2 and 3. The way I'm going to put this into words is since f of x is a polynomial, polynomial function, well, with f of 2, I'm not going to say f of 2 is -1, but I will say f of 2 is less than 0, and f of 3 greater than 0. And why do I care about that 0? It's asking me to prove that there's a 0 there. So if it's below the 0 here and above the 0 there, somewhere in between, there's a place where f of x equals 0. The IVT, do you know what IVT might stand for? Intermediate value theorem guarantees is a 0. I'll write the word 0 in the interval 2, 3. So not at least 1 0, I'll say. Now, it's not asking what the 0 is. It's just saying to show that there is a 0. Bam, there it is. I showed that there's a 0 because I connected the dots. Today was huge. Would you please check in with your neighbor? What's the important thing to remember for today? Many important things.
Yeah.
Don't put your stuff away yet, guys.
I just like.
Okay. Asher, what's an important thing for today? Yes, it is. The recency there. Jihan, what's another important thing?
What?
Are you describing the intermediate value theorem here? Let's talk about something else from today. It was a long day. We just talked about intermediate value theorem. The last part. Was there something else, maybe about multiplicity or?
Yeah. Just the multiplicity of like one,
Mhm.
and then it goes through, but it's a two objects.
Okay, cool. Anything else about that? Or you good? That was nice, by the way. Okay. Lucas, anything else?
Um, Keep in mind the two paired functions, the x squared and the x cubed.
Okay.
Like,
Nice. Yeah, that's huge. That's kind of the big idea. Anything else? What else is important to remember for today? You're rolling.
Maximum amount of turning points, like.
Is what? Oh, the degree -1. The maximum amount. It's not saying that the number of turning points is the maximum amount of turning points is one less than the function's degree. Anything else? How do you get end behavior? Is that important, do you think? The degree, specifically the not just the degree, but also the leading coefficient. Our leading coefficient. So that's right there with the degree. Was there anything else? Nothing else? Okay, get out of here. Go have some lunch. You worked hard today. Very nicely done. Just do tonight's homework on the 3 points, the polynomial.
Thank you.
My pleasure. Did that help remind you? Yeah.